Hello, my name is Sergey Gorodetsky, and I'm an associate professor at Moscow Institute of Physics and Technology. Today we're going to consider matrices and their elementary properties, and we're going to concentrate on matrices of small dimensions like 2 by 2 matrices, or columns or rows. First, let us introduce what a matrix is. After that, we'll go to operations with matrices. These are matrix multiplication, matrix addition, multiplication of matrix by a number, and after that, we'll consider the notion of inverse matrix. But I'm going to start with the definition of what a matrix is. In fact, there is nothing special in the definition. So matrix is some table made of numbers. The table can be of any dimensions. And so if it has dimensions of m by n, so we call it an m times n matrix. These are called for rows. So the horizontal ones and the vertical arrays of numbers are called columns. So in m by n matrix there are m rows and n columns. An example of a matrix can be like 1, 2, 3. It is a matrix that has only one row in it. One row and 3 columns. So each of the columns, it consists of one number only. We can consider matrix like 3, 2, 2, 5, and it is a 2 by 2 matrix. It is also called a square matrix, for it is represented by a square 2 by 2. We can have a matrix that is just one column, like 5 minus 2, 3. It is a column matrix. By the way, if we deal with coordinates of a point or coordinates of a vector, they can be written either as a row or as a column. The most usual notation used is that coordinates of a vector represent a column, not a row, but sometimes one uses row notation anyway for it is more or less the same that the two forms of writing it down, like the first one, a row form, and a column form, they contain the same amount of information. And at the same time, when one writes this notation, it occupies less space, and that's why sometimes one uses this notation instead of columns. But now let us go on to operations with matrices and how we can deal with them. There are two operations that are pretty simple. These are multiplication of a matrix by a number and addition of matrices. So when we multiply a matrix by a number, we take an arbitrary number and multiply all elements in a matrix by this number. So for example, if I consider a matrix like 2, 3, minus 5, 1, and I multiply it by number 3, I'll get a matrix in which each of the elements is derived by multiplying the corresponding element by 3. So we get 6, 9, minus 15, and 3. And there is nothing more about multiplication of a matrix by a number. So whatever dimensions of a matrix, we need to multiply each of the entries in the matrix by the number. Okay, the next type of operations is matrix addition. When adding matrices, we are only allowed to add matrices of the same dimensions. So they have to be m times n matrices, both of them. If dimensions are different, then addition is not allowed, so the result of such an addition is not defined at all. So we cannot add matrices who have different dimensions. And if matrices have the same dimensions, then we add them, summing the corresponding elements in the matrices. So for example, we have a matrix 1, 2, 3, 4, 5, 6, and let it be 5, 10, 15, 20, 25, 30. And so we just add the corresponding elements. So to get the element in the first row and in the first column, we add these two elements, and we get 6, and we proceed in the same way. So 2 plus 10 makes 12. After that, we get 18, 24, 30, and 36. In fact, subtraction of matrices is defined in the same way. So we can subtract the two matrices of the same dimensions. And if we do it so, each of the elements, each of the entries in the difference is equal to the difference of corresponding elements. So we'll get that 1 minus 5, it is minus 4. After that goes 2 minus 10, it is minus 8. And we proceed in the same way. And it's not difficult to see that we're going to get the following result. So everything with addition, subtraction, and multiplication of matrices by numbers is pretty simple. It is not that simple when it comes to matrix multiplication. I cannot say that it is very complicated, but yet it is defined in a totally different way. So first, let us find out in which case we can multiply a matrix by another one. First question about dimensions of the two matrices we multiply by each other. Let the first matrix be m times n matrix, and it happens that for a multiplication, for a product of matrices to be determined, we need that the number of rows in the second matrix coincides with the number of columns in the first matrix. So we have n rows here and n columns here. So these dimensions have to be the same. Otherwise, the matrix multiplication, the product of two matrices, is not determined, and such a multiplication is not allowed. But in general, here you can see that matrices do not have to be of same dimensions. Furthermore, if m and n are different numbers, then we cannot multiply matrices of same dimensions. Since we take another m times n matrix here, we will see that these two numbers do not coincide with each other, and so the product is not going to be determined at all. Okay, so that is the first part of the definition about how we multiply matrices. And now let's see how we calculate the product. But maybe before it, let me say first that the resulting matrix is a matrix that has dimensions of m by p. So in fact, these two dimensions, they remain, and so if we had m rows in the first matrix and p columns in the second matrix, it implies that the resulting matrix has m columns and p rows. Oh, m rows and p columns, just vice versa, as it is on the picture. And now about how we calculate each of the elements in the product. So to get some element in the product, so let us say it is situated in row number I and column number j. What we need is to take row number I of the first matrix, column number j of the second matrix, and after that we need to multiply them by each other. Now the question is, what do I mean by multiplication of a row, a column by each other? First of all, let's notice that the number of elements in this row, it is equal to n. Thus, it is just the same that the number of elements is in the column. So there are also n elements in the column. Therefore, the thing we do is the following one. We take the first element in the row and the first element in the column and multiply them by each other. After that, we take the second elements, and the second elements are multiplied by each other as well. And so we proceed, and then we take the corresponding sum. So if we denote the elements here in the row as A1, A2, and up to AN, and the elements in the column as B1, B2, and up to Bn, so the element here is equal to the sum A1, B1 plus A2, B2, and so on up to AN, Bn. And this way we calculate the element. In fact, to calculate any element of the product, we should take a row of the first matrix and multiply it by the column of the second matrix. And so this is the way the elements in the product are calculated. Now let us consider some example. Let us take a matrix, two matrices. Let the first one consist of elements 1, 2, 3, 4, and the second one consists of elements -3, 1, -2, -4. And let's calculate the product. So first we can see that, this dimension coincides with this one, therefore we can multiply the matrices. To get the element in the upper left corner, we need to multiply the first row by the first column. And so this multiplication, it yields 1 times -3 plus 2 times -2, and therefore we get -7. After that, to get the second element, we proceed in the same way. So this element is situated in the first row and in the second column. Therefore, we take the first row and the second column and multiply them by each other. So we have 1 times 1 plus 2 times -4, and by mere coincidence we get -7. Okay, to find the elements here, we multiply the row by the column, and we get 3 times -3 plus 4 times -2, and we get -9 -8, that is -17. And the final element, we take the second row and the second column, and let's see how much we get. We have 3 times 1, it is 3, 4 times -4, it is -16, and the total is -13. And this is the product of two matrices. By the way, now let's try to see what happens if we multiply the same matrices but in inverse order. So let us rewrite them once again. -3, 1, -2, -4, and times 1, 2, 3, 4. And let's calculate the product as well. So we'll get the first row is multiplied by the first column, and we'll get -3 times 1 plus 1 times 3, and we get 0. After that, we multiply the first row by the second column, and we'll get -6 plus 4, it is -2. After that, the product of a row of the second row by the first column, it is minus 2 and minus 12, it is minus 14. And finally, minus 4 minus 16, it is minus 20. What can we see if we look at the matrices? We can see that for matrix multiplication, AB is not equal to BA. Even if both products AB and BA are defined, we can see that the result of multiplication is different. So it can be different. So one can provide such matrices that AB is equal to BA. One of the examples is if we take a zero matrix, so if it consists of all zeros, I think it's clear that the product is going to be zero matrix as well, and in whatever order we consider it. So if A is a zero matrix, then both AB and BA are zero matrices. But yeah, in general, the product of matrices doesn't have the matrices do not commute if we multiply them, so AB is not equal to BA. As for addition, subtraction, and multiplication by numbers, so those operations have usual properties, that is, A plus B is equal to B plus A, and that was quite clear, I think, from the definition. But here with multiplication we have a different situation. By the way, it can be shown, and it is true in general, that if we multiply 3 or more matrices by each other, then provided that the product is determined, we can calculate the product in whatever order we like. So there is associativity for matrix product, meaning that if we're given a product of 3 matrices, A, B, C, we can first multiply A by B, and after that to multiply the result by C. Or alternatively, we can first multiply B by C, and after that the result of this multiplication can be multiplied by A. Maybe the proof is a little bit complicated in general case, but you can consider, for example, 3 matrices of 2 by 2 and prove that the resulting product is the same both for the left side and for the right side. So you can do it by yourselves. There is nothing special in the exercise. There is also a special type of matrix that is usually called an identity matrix. And it is such a matrix that it is a quadratic matrix, and it has zeros on the main diagonal. So the main diagonal is the one that goes from the upper left corner to the right down corner, and zeros are everywhere else. So these big zeros, they mean that all the elements except for the elements on the main diagonals are equal to 0. So such a matrix is called an identity matrix, and the name, let us denote it for capital I, and the name of such a matrix, that it is an identity matrix, is explained in the following way, that if we calculate an identity matrix multiplied by A, or alternatively, if we calculate A multiplied by an identity matrix, we'll have the same matrix as a result. So both this one and this one are equal to A. Of course, if A is a rectangular matrix, not a quadratic one, but it is a rectangle with different numbers of rows and columns, then these two identical matrices that are written here in the equalities have to be of different dimensions. But anyway, you can make sure by making this multiplication that the result is going to be A. Now let's consider one more example of matrix multiplication. So let us take and multiply a row by a column, and after that in a different order. So let's say we have a row 1, 3 and a column 2, minus 5. And let's multiply them by each other. So when we multiply matrices, we recall that we multiply the rows of the first factor by the columns of the second factor. So here we'll get a matrix that consists of one element only, and this element is equal to the product of the row by the column. So we'll get 1 times 2 plus 3 times minus 5. It is 2 minus 15, that is minus 13. But if we consider the matrices multiplied in different order, so here we take the rows of the first matrix, multiply them by the columns of the second matrix. So we'll have 2, then we'll have 6, so the first row, the second column. After that goes the first column and second row, so the second row and the first column, and it is minus 5. And finally the second row and the second column here. So the second row, the second column, it is minus 15. And that's the result. And so here you can see that, sometimes product of matrices AB and product BA are both determined, but they're even matrices of different dimensions. So sometimes it can happen. And as a product, we get matrices even of different dimensions. And after having understood what matrix multiplication is and how we can make it, let us proceed to the concepts of the inverse matrix. We have already introduced what an identity matrix is, and let us say that matrix a to the minus first power, or a to minus 1, is called an inverse matrix for A if A is a quadratic matrix. So the concept of inverse matrix can only be considered for quadratic matrices. And so A is a quadratic matrix, and A times a to minus 1 is equal to I, or a to minus 1 times A is equal to I. So here, in fact, it is sufficient that at least one of the equalities holds, and then we can call such a matrix an inverse matrix. So it is a matrix that if we multiply it by the initial one from any side, either from the left side or from the right side, the result yields an identity matrix. So the identity matrix doesn't have to exist for all matrices. For example, it is clear that if we consider a zero matrix, so matrix A that consists of zeros only, then multiplied by an arbitrary matrix, it is going to yield a zero matrix, and therefore it wouldn't be possible to get I. So sometimes it may happen that an inverse matrix does not exist. We won't prove any criteria for this, but rather I'll give it to you without proof, so as a fact. Now let us concentrate on 2 by 2 matrices only. So if you're interested, you may do some further reading and try to understand what can be done for matrices of higher dimensions. But now let us consider only 2 by 2 matrices. And there is such a concept, another definition, that a determinant of a matrix let me write it as matrix with 4 elements, and the determinant of matrix, it is usually denoted this way, or alternatively one can write a matrix using parallel bars, and so we can write it as AD minus BC. So that is a definition of what determinant is. And it happens that the inverse matrix exists if and only if the determinant of the matrix is different from 0. So I'm not going to prove it carefully, but I just formulate it. And now let's try to figure out the way how we can calculate the inverse matrix knowing matrix A. First, let us consider another problem. So let's say we have a system of equations. A system of 2 linear equations where x and y are variables, a, b, c, d are coefficients of variables, and e, f are constant terms. In fact, such a system of equations can be represented in the so-called matrix form. That is, we can write coefficients of variables, then we can multiply it by a column of variables, and we can get a column of constant terms. So this is an alternative form of writing down the system of equations. Indeed, if we take and multiply the first row of the matrix by the column, the first and the only column, we'll get ax plus by. And if we multiply the second row by the same column, we'll get cx plus dy. And so the left side is in fact a matrix that consists of these 2 elements. And if the matrices are equal to each other, it implies that they're equal component-wise. So the first component is equal to the first component, and the second component is equal to the second component. And from here we derive that, if this one holds, it is equivalent to the system of equations. Now let us solve this system of equations. Let's see how we can do it. First, I can multiply the first equation by c and the second equation by a, and subtract them from each other in order to get rid of x. Let's write down what is left. So apparently x's are cancelled with each other, and we'll get bc minus ad times y, and it is equal to ce minus af. Alternatively, we can rewrite it as follows. We'll see that BC minus AD is in fact equal to the following expression. It is minus determinant of the matrix A, B, C, D. So if I calculate the determinant, I take the product of these 2 elements and subtract the product of these 2 according to the definition. And here in the right side, I see that it can be written as minus determinant of the following matrix. And let us observe that matrix, the determinant of this matrix, so the matrix itself, can be obtained in the following way. We substitute the column of coefficients of variable y with constant terms. And so here on the left we had the matrix of the whole system, so the one here, the determinant of this matrix. And on the right, we do have the determinant of the matrix that results by substituting a column of coefficients of y with constant terms. Now let's call this determinant for a delta and this determinant for a delta with subscript y. And it means that y is equal to delta sub y divided by delta, provided that delta is different from 0. So we won't consider the special case when delta is 0. So let us assume that delta is different from 0. And in a pretty similar way, we can get the value of variable x. How can we do it? We'll consider the same system of equations, but this time we'll have to multiply the first equation by d, the second by b, in order to get rid of variable y. So we do multiply the first one by d, the second one by b, and we subtract them. We'll get ad minus bc times x is equal to de minus bf. Or alternatively, it means that on the left side I have delta, so it is just the same determinant. I can write it down straight away. And on the right I have the determinant of the following matrix. I have it as EF, BD. And so let me designate it as delta with subscript x. And let us observe that we get this determinant if we take the initial matrix, so with these coefficients, and we replace the column with coefficients of x with column of constant terms. And from this equality, we get that x is equal to delta sub x over a delta. So these formulas we have got, they're usually called for Cramer's rule of solving linear systems. In fact, they can be generalized for systems of equations with more than 2 variables, but we won't do it right now, and it is not that elementary at all, but it can be generalized. And now what is left is to get to know how we can get a quadratic, an inverse matrix for a quadratic matrix of 2 by 2, provided that its determinant is different from 0. So if it is 0, it doesn't exist according to the statement. Okay, so let us consider the following situation. So we have some matrix with elements A, B, C, D. Then there is some other matrix we do not know. And we need to find such a matrix that if multiplied by the initial matrix, it yields an identity matrix. So let us denote the elements in the matrix, the unknowns, as x, y, z, u, and our goal is to find the unknown variables. Okay, first let us write down the equations we have. Ax plus bz is equal to 1. So I have multiplied the first row by the first column and got this element. After that, let me write it in a different order. So let me take this product, and it's going to be equal to this 0. So cx plus dz is equal to 0. And after that, the remaining two elements. So ay plus bu is equal to 0. And finally, cy plus du is equal to 1. And now let's solve both these systems of equations, and using the laws with matrices, the rules with matrices we have obtained. So we recall that x is equal to delta sub x divided by delta. Yeah, by the way, here we can see that in effect, so quite formally, we have a system of 4 equations with 4 variables. But in reality, the system can be split into 2 easier systems, each of them being a system with 2 equations and 2 variables. And so from here, x is delta sub x over delta. So we get delta sub x if we substitute the column of coefficients of x with column of constant terms. So we get 1, 0, b, d, and we need to divide it by delta. Let me not decipher delta right now, and so I'll get d over delta. After that, z is equal to delta sub z over delta, and we'll get AC10 over delta, and so I'll get minus c over delta. And we do the same with the second system of equations, and it yields that y is equal to delta sub y over delta. And by the way, let's notice that delta for the second system, it is just the same as for the first one, for we have the same matrix of coefficients on the left. Hence we have delta sub y, it is 0, 1, b, d over delta. It is minus b over delta. And finally, what about u? It is delta sub u over delta, and it becomes AC01 over delta, so it is a over delta. Okay, now let's write the matrix we have obtained here. So if the initial matrix, if we denote it for A, it means that the one we have found, it is A to minus first, and it is equal to the following one. It is 1 over delta, multiply by a matrix D, then we have minus C here, then minus B, and then A. And yeah, as for delta, we can decipher it right now. So it is AD minus BC n times D minus B minus CA. So that's the formula for the inverse matrix in case of 2x2 matrices. So we can see that the elements of on the main diagonal are just swapped, and the elements on the other diagonal are swapped and multiplied by -1. And after this procedure, we need to divide the matrix by the determinant of the initial matrix, and as a result, it is going to give us an inverse matrix. If this delta is 0, the inverse matrix doesn't exist. I think that's all I wanted to tell you about matrices and their properties, and thanks for your attention, and I hope the material we have just studied is going to be helpful for you in future. Goodbye.